Okay, well, go ahead and get started. Gareth Morgan talked to you a couple of days ago. I was about to say yesterday, but we had a day off about Mini-RF and supporting Artemis. I'm going to talk specifically about Cabeus crater, but to revisit Mini-RF for a minute, it is a synthetic aperture radar on LRO. It operates, can operate at two frequencies, S-band and X-band. S-band is 12.6 centimeter wavelength. X/C-band is 4.2 centimeter wavelength. We have operated in two modes. We were launched as a monostatic radar, an active radar, and operated in that mode for a little over a year. The transmitter failed, although it vastly outlived its designed lifetime. And we converted to a bistatic system where we collected data by transmitting from ground stations to the moon and receiving the backscattered signal on LRO. So there's resolutions for these data. For the monostatic, it's in the range of tens of meters to 100 meters or more. For the bistatic, we're looking at about 100 meters resolution per pixel. And a key for us in pitching the bistatic mode and then continuing to operate in the bistatic mode is to look at kind of the radar scattering phase function of materials on the surface. We call it the bistatic angle because phase has a different connotation in radar, but it is essentially radar scattering phase function. And we wanted to do so because there are some specific implications for looking at these phase functions for different materials. And in particular, water ice, if present at the moon and in wavelength scale, multiple wavelength scale thickness deposits on the spatial scale that the radar can sense, we would see an opposition response, a very strong one that occurs in a pretty narrow range. We used initial data that was acquired by Mini-RF in this bistatic mode from about 2012 to 2015 to look specifically at Cabeus crater, in part because we had a fair number of bistatic observations. We had 5 or 6 bistatic observations. We had known that there was water present at Cabeus from the L-cross impact. And we wanted to see if we could see a signature of water ice there with the radar. We hadn't observed it in the monostatic phase. In fact, in looking at our monostatic data, we had determined that water ice was not present in quantities that the radar could detect. But looking back at these data with our bistatic observations, we noticed an opposition response, and one that was fairly narrow, not with a peak we would have expected to see for an opposition response due to water ice, but shown here, and the laser isn't really pointing at it, but you can see this bold line where we see a rise at about 2 degrees bistatic angle and CPR increasing, although it plateaus at a little less than 1 degree. I'm showing one of the bistatic images where these data were acquired and the illuminated portions by, in this case, the Arecibo Observatory. And it was the illuminated floor of Cabeus. We didn't really get into the PSR of Cabeus with these data, but this is in a region where water ice could be stable in the subsurface, and our penetration depth is up to 1 meter or more, so we could observe it. So why are we revisiting these data? What has changed in the time since we initially acquired and published these results? So in order to answer that, I have to go back a little bit and describe how these data were collected and analyzed. Not collected. I already told you how they were collected, but how were they analyzed? So we had 5 or 6 observations of the floor of Cabeus crater. Each observation acquired data at different bistatic angles for any given point on the surface. We wanted to combine those data into a radar scattering phase function. So we isolated regions of the floor. We tried to eliminate pixels that we thought were noise. Some are obvious. Some of these are shadow pixels. They're pretty easy to pick out. Others are low signal to noise radar data because we're looking at a very high incidence angle. And so we wanted to try and make sure we were looking at high signal to noise pixels. So we had to make some choices there. And then we just grabbed every pixel in those regions and bend them together by bistatic angle and CPR to come up with the plots we came up with. And so I'm showing, and this is from the paper, a couple of those collects and the various bistatic angle ranges we were able to collect and slowly combine into the plot that we ended up with. This was required, or we needed to do this because we had some difficulty and uncertainty in registering radar image data. It is a complex endeavor, at least more complex than it is for optical images, to properly register radar data. But we have made improvements in processing these data since that time, and can now do pixel scale registration of these data, which gives us an opportunity to look for an opposition response on the level of spatial pixels with these data, where we couldn't do that before. So what we've done for this analysis is taken all of these data, and this is showing combined 5 observations of Cabeus crater taken bistatically, and removed noise at a specific threshold. So that's why you see some holes in those data. And then we can identify pixels where we have multiple observations at a signal to noise we want to observe, up to all 5 observations in some cases. And I'll talk about the region outlined in white, which was the original region we looked at for our 2017 paper. Let's see how it shows. Well, it doesn't, it kind of shows up a little bit over there. It'll show up a little better on your screen in the back. But what we can see is when we isolate those spatial pixels, we establish a criteria for what we're looking for, which are data with a negative slope at low bistatic angles, right? So we isolate pixels that show that particular criteria. We can observe and still observe a response that is indicative of an opposition surge. It is a stronger response, more consistent with water ice than what our 2017 paper produced. So you're getting CPRs that are approaching 1 as you get to 0 phase. And so that's first off, that's good news. We can look at a plot of the data that didn't meet our acceptance criteria, and we see it does not, or maybe weakly has, an opposition response at low bistatic angle, and is more indicative of what we've observed in other data for Highlands material, which makes sense. And so this is, of course, intriguing, suggesting that, you know, there may be areas within the surface that have this strong response that we can isolate and look for what geomorphology, you know, it might be associated with, or look more closely with other data sets to see if we see matches. I will say, though, if we look at the wall of Cabeus crater, we also see some response. It's not exactly the same as what we see in the floor of Cabeus crater. It does look like an opposition response. It does start to turn over at low bistatic angles. So there's more work that we need to do. But trying to pull that together, consistent and strong opposition response for materials on the floor of Cabeus crater, and an opposition response on the wall of Cabeus crater. It's distinctly different from pixels in the same region that do not meet our acceptance criteria, which is suggestive, or the acceptance criteria is established to try to look for an opposition response. However, we have both some caveats and some things we still need to do, okay? Analysis of the data that I've shown you, and this was true of the 2017 paper and is true of what we're doing right here, assumes essentially a flat surface. We do process our data on topography, but it's very low resolution topography. At pixel scales, there are small variations in incidence angle that will affect the radar scattering properties that we receive, or of the surface, the radar scattering properties of the surface. And can also affect our determination of bistatic angle. So there is still some uncertainty here. As Jean-Pierre pointed out in his talk, Caleb Fassett recently published a paper looking at our monostatic data and trying to remove, or pretty effectively removing the, sorry, I tell Caleb not to say this. We don't remove the effects of incidence angle. We mitigate the effects of incidence angle on the data. And we can do this for the bistatic data as well, and we want to do this. It is more complicated because unlike our monostatic data where the incidence angle is essentially the same across an entire strip and for the entire strip. It varies a lot in our bistatic geometry. And also we're looking at bistatic angles, which take into account incidence and emission. So correcting for incidence or mitigating the effects of incidence angle may also change the bistatic angle for that pixel in ways that aren't related to geology. So we have to be really careful there. There's a known issue in the calibration of the data due to some cross-channel contamination. We recently recognized this at X-band. It was a long-standing issue with our X-band data. And in fact, in the monostatic phase, we didn't take a lot of X-band data because we were struggling with processing those data into images. It took a while, but we finally discovered where the issue was. We hadn't anticipated there would be cross-channel leakage in the system. Ground testing had suggested there shouldn't be, but there is, and we can correct it and have done so for the X-band. We're still working on doing that for S-band. We don't have Arecibo anymore to do additional calibration characterization of the antenna to isolate the character of that response at S-band. We expect it to not be as much of an issue as it was at X-band. We do have a smaller dish that we've been doing calibration attempts with that doesn't normally operate at S-band. So we're also trying to validate their system before we move to revalidating ours. But we are working on it. It's an active thing for us. And also we need to expand this analysis to other regions of the poles. I wish I could tell you we have other regions where we might suspect water ice, but in that S-band bistatic phase, we were working hard to get data of Cabeus. We don't have a lot more data of polar crater floors that we suspect water ice might be present, but we do have a lot of these bistatic data that can help us get more context and characterize whether these responses occur anywhere else. We didn't observe it in the 2017 paper when we were looking in bulk, but we want to go back and start looking more widely across these data to see if we see it at spatial pixel scales, so we can determine whether it's truly isolated, in this case, to the floor of Cabeus crater. And we're on that. We're also collecting data at X-band. Last year at DPS EPSC, I presented results with similar techniques for that. We still don't see a response like we see at S-band, which could suggest whatever we're observing is deeper in the subsurface than X-band can penetrate or observe. But stay tuned. It's been slow going. We're picking up the pace now that we have corrected a lot of these issues, and we're looking forward to getting more of this work done. Thank you.
Thank you so much. Yeah. And we do have time for questions. I don't see any, so thank you very much. Let's move on to the next and last talk in the morning session, which is by Kusei Toyokawa. And he's talking about indigenous water and pure and anthracite outcrops on the moon observed by Selene.